Trying to say I hope everyone's ready for a wild ride here because this problem's got some twists and turns in it. It says the density of nylon is 1.15 grams per centimeter cubed, and nylon has a shear modulus of 8 times 10 to the 8 newtons per meter squared. If a 0.75 centimeter thick layer of nylon is being dragged at constant speed over a surface with coefficient of friction 0.8, all of this is shown below. What shear angle do you expect? Now, maybe to make clear what's being asked for here, if I kind of draw, I'm going to draw like maybe an excessively thick version of this layer. Maybe it won't be quite as long. And maybe I'll exaggerate the amount of shear that's really there. But let's say this represents that layer being dragged along here. Here's the force being applied. And in that sense, like if normally this edge of the layer were just vertical, but because of the shear, what's happened is it's been deflected by an angle phi. There is that angle phi right there in the picture. So that's what we're being asked for here. And maybe one thing we can do to relate to that is to state that in terms of that shear angle, the definition of the shear modulus is thinking about stress over strain. But in terms of strain and in terms of the shear angle, it was just equal to the tangent of that angle. So that's maybe a formula we could start with here. But there's some issues I think that kind of come up here, because if I start to look at like the quantities that I'm given a density for nylon, and that's equal to that 1.15 grams per centimeter cubed, which maybe, I'm not going to spend all the space here to show this, but you could maybe work this out yourself, that this is equal to 1,150 kilograms per meter cubed, so converting all that into base units. We're also given the numerical value for the shear modulus of 8 times 10 to the 8 newtons per meter squared, so explicitly seeing some familiar units there. What is this 0.75 centimeters all about? Well, I think in relation to how we normally describe shear going on, is I think that would be equal to what we would call H. I'm just going to say H for like the thickness or the height of the layer. Kind of makes sense either way. So that's 0.75 centimeters, which I'll convert to 0.0075. Of course, we just read all this. You might say, huh, this is kind of maybe pedantic to list all this stuff, but I like to have it all written down because it's going to help me to think about like what to do next. Because one of the issues that I'm kind of stuck on with this, sometimes I can do a problem and just read off the numbers and start plugging into a formula. And this totally doesn't look like I can do that, because like what's missing? I don't have anything for F. I don't have anything for A. The thing I'm actually being asked about is this angle phi. I didn't write that anywhere. I'll just keep that in my mind because I don't want to waste space here. But it's hard to connect this formula that I have with all the stuff that I'm given here. So what can I possibly do? Well, maybe a force analysis. I mean, there's friction going on. This thing is moving. There must be forces involved. So maybe I could do some kind of force analysis of this situation. So let's start something like that. And in that sense, I think I've got force of gravity. So I'm thinking about the nylon layer, all the forces on the nylon layer here. There'd have to be a normal force. There's the applied force F that's shown in the picture. And there'd have to be a force of friction, which, given the fact that this layer is described as being dragged at constant speed, I think that force of friction, just like normal force balances the weight force, the force of friction must balance the applied force. And in other words, when I say like, well, hey, F net is equal to 0, that kind of implies two things here. We could maybe look at this as coming from component equations, but I think just looking at the picture, we can see that the force of friction has to be equal to the applied force F, and we can see that the normal force must be equal to the force of gravity. So I can kind of draw those general conclusions. Another principle I could maybe apply to this, because again, there's coefficient of friction there. This thing's sliding along constant speed. It doesn't really matter what speed it's going, though. We know that the force of friction is equal to that coefficient of friction times the normal force, which we just said is equal to the gravitational force, which I could further state that explicitly in terms of maybe some quantities that maybe I'm crossing my fingers I might have. Are any of these on the list I just wrote? Well, mu is, but m is not, and g is not, but that's okay because we know it's 9.81 meters per second squared. So have I made progress? I don't know. Maybe not as much as I'd like. But I think where I could go a little bit further with this is recognize that since I'm given density, and density is mass per volume, this mass m could be thought of as density multiplied by volume. So in other words, I'm going to write down here mu, and then I'm going to, in the next space here, I'm going to start with rho for density and then multiply by volume. But what's the volume of this nylon layer? Well, it has a height h, and we know that there's an area here in the shear modulus formula, and that's really this area right here, right? And remember that h is, right, this is h. I didn't really leave a space here, but there it is. That's h as we imagined it. Those two multiplied by each other should be equal to the volume of this thing. So I'm going to say rho a h can replace the mass m, and then we still have to have that g there. So the overall conclusion I might draw from this is, since force of friction is equal to this, but that's equal to that applied force F, is it means F, and that applied force really is the force that is the same as what's in the shear modulus force here. So F is equal to mu rho a h g. And maybe what I could do now with that is I could take this expression and plug that into the formula for the shear modulus. So that would say that S is equal to mu rho a h g over a. Now, why did I do that, right? You'll notice those a's cancel, and we're getting a little bit closer to a formula where maybe I know more of the parts. So I've got, that's all the twists and turns I had to go through to get to something like that here, is I can now kind of go through and compare to my list of numbers, right? I've got mu, there it is, 0.8. Rho is equal to 1,150 in standard base units, right? H is equal to 0.0075 meters, we said. G, of course, we know is equal to 9.81 meters per second squared. The A canceled, so that's gone. And we're looking for phi. And S, we also have a number for. So surely I must be able to do something to solve for phi here. It looks like maybe a simple thing I could do is cross multiply and say that tangent of phi, if I multiply both sides by tangent of phi, divide both sides by S, tangent of phi would be equal to mu rho h g divided by S, which that would imply that phi is equal to the tangent inverse of all that stuff, mu rho h g over S. And I think, fortunately, I might have enough space here because I want to write down all those. I've got a lot of numbers to write in here to say what I'm going to put in my calculator. 0.8 multiplied by 1,000. 150. Maybe I'll leave all the units alone here. I've already converted everything into base units, or things derived based on base units. So if everything works out, it should be fine. And part of the argument with that is that overall, the number that I put into a tangent inverse should be dimensionless or unitless. And so if everything is in base units, it should all cancel without any other needed conversions because I took care of all that up here. Sometimes this can be a little, like doing the method I'm showing here is something to be careful of. If I had more space, I'd maybe check it and write all the units just to be sure, especially if I got the wrong answer. I'd probably want to do that, right? But it definitely saved me enough space to be able to get all this in here and to show explicitly what I'm now going to put into my calculator. And when I put that into my calculator, I get like 4.8 times 10 to the minus 6. 2 sig figs, probably good, right? So I'll just put down 4.8 times 10 to the minus 6. Barely got space there for it. Okay, maybe I'm ready to check the answer. Oh, wait a minute. What did I do here? Was it the units thing? Could it be something else? What did I forget to be transparent about? What mode is my calculator in? Oh my God, it's in degree mode. And You know, I don't know if I got enough space to put a little degree symbol here. Okay, I'll throw it up there, kind of. Yeah, it's in degree mode. So I actually probably should take that number now and convert it into radians. Or maybe I redo the calculation, putting my calculator in radians mode. I mean, actually, it's fine as long as I say it's degree, right? But I'm going to check, put my calculator in radians mode, and then I get 8.46, like 1125 times 10 to the minus 8. So in other words, I do get a number in radians, which maybe, you know, that is probably the better unit to use for this type of a situation, maybe. Actually, I don't know if that's really true. It's just as long as you put the degree symbol, that'd be okay by me, either one. But again, I put it here in radians to make that clear. But maybe one of the things that this really does illustrate is it is a common pitfall to one of the other common pitfalls is to forget to check what mode your calculator is in. In this case, it wouldn't have been so bad if I'd left that number, as long as I'd remember to put the degree symbol in this class. If I were grading that, I'd be okay with that. If we're doing an online assessment, though, it may be harder to put that degree symbol. Maybe I'll state in there, will tell me which one you used in some way. But you got to be transparent. The convention, though, handwritten, is to have that degree symbol, and if there's nothing, it means it's in radians. But again, I put that here in the slide to make it super, super clear. And it'd be good to be transparent about our answers in either case.